Okay, Cup. Welcome to the 8th or 7th? 7th. Okay. Welcome to the 7th class of the summer pre-course, Interactive Mathematics with Mathematica. Last week, we had gone over the basic idea of calculus, in particular, differential calculus, essentially, trying to find the rate of change. Graphically, that means trying to find the slope, right? And the opposite of that, okay, so differential calculus is a little bit like division, but instantaneous division, okay? Take the height, divide by the width, but do it at a small width. The opposite or the converse of that is like multiplication, takes height times width, which in calculus is the powerful means of calculating cumulative changes, right? So instead of trying to find the rate of change, you are given the rate of change and you're trying to take stock or take account of the accumulated changes as a result of that instantaneous rate of change. Graphically, that corresponds to what? That corresponding to taking the area under the curve. Okay, so we talk about that. So the concept, can keep that analogy in mind. Okay, one is take the height, divide by the width, but take the width be as small or ultimately zero thickness. And the opposite of that is multiplication and adding the cumulative strips of multiplication. But instead of multiplying big height, one height by the whole width, you multiply height by instantaneous width and a little bit at a time, and you add them all up. Okay, and that's going to give you what? That's going to give you the precision that's not possible before, right? And that allows you to work in cases where the function you have is not straight line, basically. Okay, so that's where calculus comes in. Now, then we talk about, well, given that, what can you do with calculus? Well, it gives you the power to model stuff. Right? It gives you the power to model stuff because sometimes you model some quantity because you can relate that quantity to its derivative. Okay, so that would be like in physics, that happens a lot, right? You have what's called differential equation. Some position is in an equation. You have a position, you have some constant, you have velocity, you have acceleration. It's all in one equation. That's how you model reality. And also calculus gives you the third power. So power of precision, right? Power of precision, power of modeling. And the third one is power optimization. What it means is that sometimes there are things you want a lot of, as much as you can. So you're trying to maximize. Sometimes you have some quantity that you want to have as little of it as possible, like cost. And that quantity depends on other quantity. In mathematics, y depends on x, right? And you want to maximize y, get as much y as you can by changing the value of x. Or conversely, if y happens to correspond to cost, you're trying to get as little y as you can by changing x, okay? And that's the optimization thinking. Now, I gave you an initial flavor of solving this kind of optimization, right? One is to say something like, well, you're at the top of the hill or bottom of the valley, you know that because you happen to have zero curve. So you kind of solve for it in a way, try to find the slope, set the slope equal to 0 and find that location. Okay. On the other hand, most of the time, you actually can't do that. You can't directly jump to the conclusion. You have to move a little bit at a time as if you were trying to find the valley, at the bottom of the valley or the top of the hill by starting at some point, somewhere in the forest. And that's when I introduce you the concept of gradient descent, right? Or this kind of algorithmic thing where you take a kind of gradient measurement, right? And you move around the 360 degree, which direction gives you the biggest, steepest direction of descent if you want to go down, or ascend if you want to go up. And you just take one step. Then you evaluate your gradient again, you take another step, and keep doing this. Hopefully at some point you get at the bottom. Okay. Now in real life, there could be false bottom. You guys know what a false bottom is, right? So you go to the bottom, but if you go up a little bit, you can go down to a bigger valley. Okay. So that's called local minimum. That happens as well. So might as well use the blank. Good. Okay, so we have this thing where this is a function, right? And you take a small slope, that's differentiation, right? If on the other hand, you actually given the slope and you're trying to find the total area, so, okay, you add them all up, right? Over, right? But this thing becomes smaller, so become dx, and this thing becomes this integral sign, okay? And this is y in here somewhere. Okay, right. So that gives you precision. When you have something like a position, say x, and dx, dt, say, and the dx square dt, that's a second derivative, okay, in the notation. So that would be like position, velocity, acceleration. You have all this in some kind of equation that becomes differential equation. So you solve for that. And the third concept is, like I said, let's say you want to find the top or you want to find the bottom. Okay, you do this. You can solve for it directly, right? That's a spot where it flattens. But in real life, this is not going to be just one dimension. I'm teaching you calculus in one dimension, but you have gazillion dimension. In fact, we show you example of 2 dimension, right? So in 2 dimension, it looks like a little bit like contour plot, and you kind of like take a step, gradient descent until you get to the bottom. So that's where we are today. Okay. Now, if you understand this concept, okay, and this is my game plan to you. If you understand that when you need to understand the rate of change, that's differentiation or differential calculus. You understand that when you want to find accumulated something, anything, it is integral calculus. Take this integration. When you have some kind of dynamic model of how things evolve over time, you know, like for example, the rate of COVID infection, for example, that's when you get into the realm of differential equation. Finally, if you have some kind of objective, some kind of things that some function you want to maximize. Okay. So if, you know, if you are, say, very business minded, from the very beginning, you think of this in terms of economic or financial variable. That's fine as well, right? So this could be a marginal return for whatever function, production function. This could be cumulative profit or maybe risk. You do that as well. We'll show you that today. And you can think of this as evolution of something. Okay. Now in finance, you would use this, but only in a very complicated way, like financial engineering. I talked to you about this Black-Scholes equation. But in most finance, you know, like putting money in the bank and so forth, usually it's not taught in terms of partial differential equation. That's fine. Economics, you certainly do that. This is how they model inflation, or all kind of stuff. It's you know. Finally, you can think of this as a profit or cost function. Okay, so this is something that's, you know, as long as you understand the context of your problem, the nitty-gritty mathematics, you don't have to do it yourself. Okay, numerically, you can use Python, but occasionally you want precise analytical answer. You can use Mathematica, right? So remember, dy dx, right? So y is, let's say, I'm just going to put in general form, df of x, right? How do you write it in Mathematica? You write d, open bracket, f of x with respect to x, right? Usually it's going to give you something that's analytical. So maybe in ratio. If you want actual number, you just put n in front of it, right? Likewise, if you have an integration problem from a to b, right? F of x dx. Again, now I'm expecting all of you who haven't had any calculus to understand this. Okay, so you haven't taken a single course in calculus in high school, but from last week, you must know what this is. This is the cumulative change, right? Cumulative change in this quantity, okay? And that quantity is some kind of f of x, and this is your x, and you go from x is equal to a to x is equal to b. So if you're talking about cumulative change, graphically, that is the area, okay? This, in Mathematica, will be written integrate open bracket f of x, comma, curly bracket x, a, and b. Okay, you saw that. And we saw how, arbitrarily complex you can do this. So I'm not going to spend time doing that today. Okay. Instead, today, I'm going to start off by giving you a little bit of, it's kind of a talk. I kind of wrote it down as an essay, but this is to understand that everything you do is modeling, okay? On the left-hand side, when you're trying to model the derivative, I told you the calculus give you power precision, power modeling, and power optimization, right? But actually, everything you do is called modeling. Optimization is itself modeling. What do I mean by that? Okay, what do I mean by that? So today is if I were to give a lecture today, a name, it'd be something like what has everything got to do with modeling, and what does mathematics have to do with modeling? Okay, modeling. Okay, we alluded to that a little bit last time. We talked about the catwalk model and all that, right? Okay, fine. So the first thing I'm going to say is this. Human beings, all of us, the reason we are here is not because our ancestors were stronger than their competitors, like Neanderthals. We live in the same time as Neanderthals and other hominid population. You can say that we were not stronger. We were more adaptive. And that's the whole story of evolution. We were more adaptive, and therefore we can evolve with, situation and blah, blah, blah. But if you get down to the nitty-gritty level of an individual or as a human race, what is our competitive edge? It's actually our ability to predict better than other people or other species. Now, what do I mean by predict? Today, if I'm talking about predict, right, you hear things like predicting the result of an election or something like that, something far-flung like that, predicting comet and stuff. No, I'm not saying that at all. Okay? Pre is a prefix, means before, okay? Dict is also, well, it came from a Latin word, but it has the same root as dictionary, right? Dictation, diction, dictum. What it means is some kind of statement. So predict just means you say something before you have direct evidence of that thing. So if you look at the sky and you see the cloud forming and you say it's going to rain this afternoon, that is a prediction because you say rains before rains. That's it. Okay, that's given us all the evolutionary advantage vis-a-vis other species. Okay, now all I'm trying to say is that pretty much, and you can debate with me philosophically with this, I can say that 99% of your cognitive function is prediction. Okay. If I overhear you saying, let's say, nice thing about you, okay? what is your next, what's your cognitive conclusion? Chances are I'm going to conclude that you're going to feel good about yourself or whatever, right? Well, that's a prediction, right? What's my input? Input is I observe the situation and I know what's going to happen next. So just about everything involves prediction. Now, some of the prediction is so built in that you don't even think of it as prediction. Like if I toss this thing up, right? The information is how fast is this going or whatever, where it is at certain speed, right? And what's my prediction? Where is it going to be? But because I have done this loop 1,000 times in life, I can do this almost without thinking. But that's prediction, right? Oops, sorry, I just did a bad prediction. But a good prediction would be I toss the ball one way and I can catch it here because I know it's going to be here, right? Everything you do is prediction. So that's the first thing I want to say. Now, if prediction has been so powerful for your evolution, it's actually also the most powerful thing in your profession. Because at the end of the day, just as we outlived our friends who were Neanderthal, right? We outlived the Neanderthal. They're all gone. Okay. Sometimes there's some interbreeding or some genetic trace of Neanderthal in the European population, but most of the practically we can say we outlived the Neanderthal. They are dead. Okay. Likewise in business, your business can outlive your competitor if you make better prediction. And again, prediction in the most generalized sense of the word. I'm not talking about you in the business of predicting stock market and two of you are competing, so you have to predict. No. Every single thing, every cognitive, analytical problem you face in business is prediction, right? You are going to predict that you are going to be able to sell this thing to a client. There's going to be a market of certain size. You are predicting that with some degree of certainty that you are going to be able to get these supplies of raw material. You're predicting that under supply chain disruption, there's going to be a hike in the price of something. So you have to find alternative source before people realize what's going on. And if you didn't, you got a business. So all this survival based on prediction. Okay, so two things. Okay, just so I've said already two things. The first thing I said was just about every cognitive solution that you come up with your head is a form of prediction. Okay, it's a form of prediction. Second, prediction, just as it's allowed human to outlive our Neanderthal peers, prediction is gonna, a good prediction or better prediction is gonna mean life and death or difference between your business or your project or your innovation succeeding versus becoming another junk startup. Okay, so prediction is just about everything that your success hinges on this. Okay, now let's gloss over this. Okay, but here's the thing. Okay, I'm gonna put first. Well, let's do this. You don't have to look at this text. It's just okay. Just reminding for myself. The way we make prediction analytically is nothing more than what we saw before. Y is equal to f of x. Okay, y is equal to f of x. What makes y equal to f of x a prediction? Okay, so let's go to the board. Okay. Now, when I say A is equal to B, you guys learned that, right? From Mathematica, there are two meanings, right? There's this A equal to B and there's equal to B, correct? The second one is a logical, is asking, is A equal to B? What's the first one? Is A is set to B, okay? Well, those are what we use in programming, okay? But for now, I want you to forget about that concept, okay? Forget about that concept. All I'm doing is this. When I say the left-hand side is equal to the right hand side, I'm neither asking, this is question. So I put this question, like a question mark. This is an instruction, so I put in this thing. Okay, so it's an instruction to set A equal to B. Here is a question mark, is A equal to B? Now, I want you to forget about this concept of equation and go back to pure mathematics. Pure mathematics, left-hand side equal to right-hand side is a statement. Okay, it's a statement. It's like saying A is equal to B. But if you say A is equal to B, is it? That becomes a question. A equals to B. If it isn't, make it so. That's assignment, right? But I'm just going for the first part, just the very first part. It's just one statement. I'm just saying that A is equal to B. Okay, are you guys with me on this, right? Very neutral, very neutral. Could be false, could be true. But all I'm doing is using this as a verb. It's saying that the left-hand side and the right-hand side, actually the two meaning of equality in this sense. One, it's the same thing. Okay, so when I say something like my TA for this class equal to P proud, it's actually the same person. Okay, so it's identity. It's identity. The other one is to say the weight of this share is 5 kilograms. So if I take the weight of this share and something else that weighs 5 kilograms, I wouldn't be able to distinguish them. So it's quantitatively indistinguishable, quantitatively. Okay, so that's it. All I'm doing is left-hand side to go to right-hand side. And let's change the color just to make it nicer. Now, what do I mean by this? Okay, y is equal to f of x. Okay, in fact, that's the whole thing of mathematics, right? We do this. Okay. This is saying that the left-hand side is equal to the right-hand side. It's a statement. Statement. Okay, so mathematics is not about making prediction. How do I turn this into a human activity of making prediction? Anybody? How do I turn this into a human activity? Okay, I told you that humans are very good at prediction. Well, I'm not saying that other animals don't do prediction. They also do that. They're just not as good as us. Okay, Neanderthals also made predictions about weather and whatnot, but we were just probably better. Okay, this is how it works. Okay, this is how it works. Okay, when I say left-hand side is equal to right-hand side, there's a symmetry, right? Left-hand side equal to right-hand side is equal to left-hand side. With prediction, it's not. There's an element of before and after. Which comes first? The right-hand side or the left-hand side in this case? The right-hand side, right? The right-hand side comes first. Now, there are three things in there. There's y, there's an f. In other words, you get f of x, then you say y is equal to that. Okay, so you do computation first. You calculate f of x first, right? That's exactly what prediction I mean. For example, x is equal to dark cloud. Okay, f of x is equal to dark clouds should convert to rain in 2 hours. Y is equal to rain in 2 hours. Okay, now let me be a little bit tougher on you. So the right-hand side comes before the left-hand side. Next question. What about x and f? Which one comes first? Let me beg to differ. Okay, actually, it's a trick question. It's a trick question. If you think about it, before you see dark cloud, you have human experience. That human experience allows you to say dark clouds now equal to rain 2 hours later. So actually, whether or not that day has a dark cloud, you already have that knowledge, right? So in that meaning of the word, F is very general and it's there first, as if it's always been there. You've always been able to say dark clouds equal to 2 hours later it's rain, whether or not it has dark cloud right now. Now I'll come back to you why X come first in another context, but very good question. Keep that in mind. So what happened is F come first. Ability to say dark cloud now, rain 2 hours later. Then for particular day, once you got this, somebody tells you, hey, it's got dark cloud. Now you have 2 ingredients, you get this. So it is 1, 2, and 3 in that order. Okay. So whereas mathematics, left-hand side equal to right-hand side is very symmetric. Okay. By the way, assignment is not symmetric, right? You set the right-hand side equal to the left-hand side. Oh, sorry, you set the left-hand side equal to the right-hand side. This is also not symmetric because this comes first, comes second, comes third, comes third, right? Now, hoping maybe. Okay, so let's think of okay. I'm using square bracket like Mathematica, but really not really. That's not what I meant. The reason I use square here is I want to give you the notion that it's a box. It's a box. Okay, so it's a little bit like this. You have this thing. Somebody plops in X, and you get that. So this is kind of like an arrow. Okay, it's an arrow. I want you to think of it this way. Okay, okay. Now, so if this is prediction, remember today we're not talking about prediction. The name of today's lecture is what's modeling got to do with anything, right? Tell me, what is modeling? In this picture. Okay, I told you that prediction is when you start with an F, you've got an F, general F, general case. You have specific X, you plug specific X into a general F, you get specific Y, right? And that could be, any kind of complicated function, linear, I don't care, right? So that's prediction. I'm telling you now that the reason that you are in this education program, this very, arts and science, and to give you competitive edge. One of the most important thing is to recognize that you can only make better prediction if you're using a better model. Think about it, okay? Same cloud, but you know that black cloud leads to rain 2 hours later. Somebody else has a bad model, okay? Rain clouds equal to sunny later, but in this case, maybe after the rain, it's sunny, but let's say it's a bad model. Who is gonna win? Somebody who sells an umbrella or someone who sells outdoor ice cream, right? You are going to make money because you are going to sell umbrella, right? Somebody who sells outdoor pizza or something like that, that's not going to make any money because it's going to rain. Simple as that. Okay. So what you want is you want better model. Okay. You want better model. Better model gives you this. But this is the outcome of this and this. Okay, so I'm going to rewrite the equation again. Okay, y is equal to f of x. Okay, I want a good one. So this is good versus bad. I want a good one. Why that's good? Why that's accurate, right? my question to you is, again, you're going to build a model. Okay. And for now, I'll just say the model is F. It's creating an F on X that gives you Y. Okay. Let's think about criteria. Let's think about who is responsible for that. Okay. Let's talk about responsibility first. Responsibility. What do I mean by that? Okay. There are 3 professions in life that you're going to rely on. One's a mathematician. Okay. He's responsible for creating the F. Right? In fact, sine function, cos, this has been done for you. Okay. So, you know, give mathematicians a break. I mean, they've been working for you without pay for thousands of years. Okay. So, mathematician gave you this. Gave you this. Who gives you this? The data professionals, right? The database programmer, data engineer, people who do all the sweeping. So these are data professional. D guy, Mr. David, data professional. Matt, the mathematician. David, the data professionals. Right? What else you need? Well, you have a calculator, right? Somebody has to build that calculator for you. Except your calculator now is a lot more complicated than that Casio calculator, right? So you need a way, even if you know the math and you have the data, you still need to do the computation, right? So I'm just going to kind of stick somewhere here, a third guy, Chris, who's a computer engineer, right? Now, so these are the guys who are responsible for you having the model. Okay. Now I'm going to move on. What makes a good model, right? Right. It's good. Well, and when I say a good model, I can mean generically a good model, or you hoping to have a model that's better than your competitor. Okay. So what makes a model good? Anybody? Well, I'll give you 3 English words. Okay. 1, it's accurate. Right? Accurate. That means, yeah, I'm going to predict it's going to rain. It's accurate. Right? So accuracy. The other one is a little bit harder to understand. Precision. Okay. And for now, just think of it as consistency. Okay. If you're right, you're consistently right. If you're wrong, you're consistently wrong. Okay. And the other one is speed. Okay. Now, let's say computer engineers, you know, using NVIDIA card and all that, takes care of this. Okay. So for this class, I'm not going to talk about speed, but certainly you have a better model than your friends if you have a faster speed. Okay. Speed is so critical in a low latency application. Okay. It's just not covered in, you know, mathematics pre-class, but it is very important. By the way, used to be in the old days, somebody really made a lot of money in the United States. You know how he did it? Free money, literally guaranteed profit. You know how he does it? There's some kind of market, mercantile market in Chicago. This guy sits in New York. Okay. Normally they'll use some kind of, I don't remember the detail, but let's say it's a very slow telegram. This guy used a high telegram. So what's happening in the market in Chicago, he gets information first, faster than other people. And he buys that thing that is going to rise in price. By the time everybody gets the same information, he already bought everything, right? It makes a lot of money. This is true. This is historical. This is, you know, 150 years ago, maybe. Okay. So I'm not going to talk about speed, right? I'm not talking about speed. Well, I'm going to talk about accuracy and precision. Precision is a little bit like this. Okay. Now, well, I'll make it even simpler than that. If you get one shot, okay, it's accuracy. It's accuracy. Okay, you want more accuracy. There's no meaning of precision because it's about consistency over time. But if you get 3 shots, okay, this is a high precision, meaning you always hit the same spot, but it's wrong, right? On the other hand, so this guy, 1, 2, 3, versus this guy, 1, 2, 3. Let's make it 4. Okay. This guy has very low precision, but the accuracy is good because when you take an average, it's in the middle, right? This guy is good because he's consistent. Now, who do you like better? Who do you like better? Depends on the relationship. If the relationship is short term, I want this guy because at least he's sitting something. But if the relationship is long term, what do? Okay, you're doing good. Next time, aim lower and to the left, right? So it depends on the application. Okay? So this guy, you can move it over here. Where this guy, you don't have to move him anywhere, but he has to work on his inconsistency. That's a little bit harder. Okay. So in modern engineering, precision matters more than accuracy. But that's only if you get to iterate your process. Once you get to machine learning application, a lot of time you don't get to repeat all of that. Okay. So your accuracy becomes the first thing that you have to go with. And sometimes there's a trade-off. It's not sometimes, it's always a trade-off between accuracy and precision. Okay. But anyway, I'm gonna leave it that. So these are the things that you want to do. Okay, let's go back to this. Y is equal to f of x. Okay. Now, I already forget about computer guy who allows you to calculate this accurately and fast. Okay, let's just say that's a technical thing. That's beyond you. Now we talk about modeling. Okay, modeling. Okay, when you get to data science, like data analytics, you are actually working on this and this simultaneously. It's a little bit of a chicken and egg. What comes, what do you, if you have a better model, you need a better data. If you have a better data, you have a better model, kind of things. So it's always model, data. It's quality of both working together. Okay. So in data science, and this is, by the way, this is the art and science of machine learning. This is where, you need whatever, get to stuff I know, stuff I do. Okay. But for now, let's say you have no choice. Let's just take away the responsibility again. Let's forget about the data guy. Let's say the data guy already gave you X. Right? If the data guy is already giving you X, that's your job. Okay? That's your job. That's your job. Okay, that's your job. How do you do it? Okay, I'm just make one comment and let's take a bathroom break. This is where's your friend came in. Okay. You don't start with knowledge, F. In real life, X comes first. In real life, mean in a professional life, because what happened is this. This is how your data comes in. X and Y, I going to 1 to whatever, 1,000. Okay. Now I told you the mathematician has done their job, right? They gave you the best function in the world. The point is mathematician gave you too many functions. In fact, mathematician give you infinitely many functions. Your job is to select the F that best fits this thing. So yeah, go back to a real life. What comes first? Not F, X. In fact, X and Y. And that's what we mean by, supervised learning in machine learning. Okay, you get X and Y, and let's say, iteratively you pick F A, and that gives you Y that's very bad, it's far off. You try F B, that's a little bit better, and you keep doing this until you get to F Z. Okay, the final iteration of your model gets very good. For that, then you hope that now this is in the past, you've seen this. Now the next day you get a brand new X. Hopefully you will get the Y right. Okay, that's your modeling. So even though the mathematicians have done the job of building all these amazing functions, Mathematica has a gazillion functions in there. Mathematica is not going to tell you which one to use, right? You have to choose. And well, with machine learning, there are a way of asking Mathematica for it. So that's kind of like a cheat. But let's think of it this way first, before we go to the break. Let's think of your job as to handpick F. Okay? Your job is to handpick F such that it reflects your experience, so that hopefully you're still living in the same universe as you were before. So when you see dark cloud, chances are in the past, dark clouds now mean rain 2 hours later. You're going to make that prediction again. And the world hasn't changed. The clouds, the way clouds work, it's the same. So hopefully you're correct. Okay. So why are you better than your friend? Well, first of all, again, there's a speed. I'm going to forget about that. There's a quality of data. I'm going to forget about that. But right now we're talking about the math part. It's the selection of F. But it's not just one. F is not a basic function. It's not exponential, sine, cosine. It's a combination of them. Okay. So you may have to choose, well, the best F is x squared minus log of x plus 2x to the 7 square root exponential x. I really don't know. I don't know. Okay. The point is, mathematicians have done this for you. You have done the components, okay, and tells you how to put them together. You, as a chef, let's say, okay, so mathematician tells you how to fry eggs, how to do this and that, but you can come up with the dish by combining all this little complicated, and that's your job. Now, the only thing that differs now is that this thing is so complicated. Okay, economists used to have to come up with this thing by hand. And it's very hard, and they have to make some kind of reasoning. As people get hungry, they get more desperate, but if they get more desperate, they're more willing to forego long-term health for short-term consumption. And so maybe it's one function over this square or blah, blah, blah. They have to handpick by hand and then try to see if it fits by, allowing this coefficient to fit the data. The difference now is that with machine learning, you have a very generalized form of math. Some math, very big math, very complicated math. And then think of it this way. How do you make this function more complicated? Let's do this. Let's add all the conceivable functions in the world. Okay, there are a million functions. And you add a component, A, FA, plus B, FB, right? And how much of A, how much of B you choose, let the computer try. That's where machine learning comes in. Okay? And this is where right now, once you get to this understanding, I don't care if you go to applied digital intelligence, healthcare, in your application that requires some kind of model building from X to Y, given some kind of historical precedent, you can ask a machine learning to do it for you. Okay, so your job is much easier than economists 50 years ago. Okay, they have to think, hey, what make people pay more? Well, what make people, that sort of thing, right? That's economic modeling. They have to think and then they have to test. Well, in this case, the thinking is kind of like, well, you know what? Let's try them all. Now it's a little bit, it sounds a bit of a cheat, but a lot of time that's all you can do because the function is so complicated, guys. Even if you have a real underlying function, you would never in a million years figure it out. And that's where the power of machine learning comes in. Okay, but that's you with learning algorithm. But at the end of the day, the job is modeling. Okay, now let's take a 5 minutes break. Jacob, welcome back from the break. Right. So before the break, I made the case for you, in sort of like steps of reasoning. Hopefully you buy the argument. Number one, just about every cognitive analytical function or problem you solve throughout the day as a human being is some form of prediction, quote unquote. Okay. Like I said, prediction in the most general sense of the word. If you toss the ball from your left hand and you catch it with your right hand, implicitly, there's a prediction function of what's going to happen to the ball once you release it from the left hand so that you can anticipate and put your right hand where it's going to land. Okay, so again, nothing big, not difficult prediction problem, but I'm just trying to frame all kind of analytical cognitive problem solving that human beings do in terms of prediction. And second step is I make the case that, maybe ability to make good prediction from the set of information is what has empowered our evolutionary ancestor, hundreds of, maybe tens of thousands or hundreds of thousands years ago to outcompete other hominids. Okay. And just like that, just as there's an evolutionary survival value to making better prediction, for the species, ability to make a better prediction. Also, if you think selfishly, so to speak, of just your own self, your own career, your own project, your own innovation, your own startup, what's going to allow you to survive where other business, other startups fail is the ability to make better prediction. Then I link that, let's say I annotate the concept of prediction with an equation. Okay, y is equal to f of x. But whereas, in mathematics, in computing, y equal to f of x is an assignment, or it's a test, it's a logical test. Is it equal? Is the left-hand side equal to the right-hand side? Okay. Assignment, left-hand side is set to equal to right-hand side. In mathematics, it's very neutral. It's just saying that left-hand side is equal to right-hand side. But when I use y is equal to f of x as a notation, as an annotation for the human cognitive process of making prediction, implicitly, right, I am assuming that the right-hand side comes first. You have f, you have x, then you have f of x. That's what you predict. That's your prediction for y. Okay. And make the general case that, mathematics or the general function f come first, right? And then you supply with specific x, and then you get specific y. But ultimately, nobody gives you the f, right? You have to create the f or choose the f that best fit your data. Well, your data comes in the form of x and y. So you choose the f that best matches historical evidence for how x and y pair up. If you see this x, you see that y. You see this x, you see this y. You see that x, you see that y. And then from there, you choose from among a million function mathematics has allowed you to build just one of them. Hopefully that one is good. Yeah. But then I fast forwarded to today, which is where you don't actually handpick the function yourself anymore. You ask the computer algorithm to try to sift through all the combinations and try to come up with one that best fits the data. Okay, very good. Now, what I want to do now is just to tell you that these are basically all the models you're going to have in real life. These are the kinds of model, okay? They're not exclusive to one another. The first line is not, doesn't exclude one. So again, the concept is y is equal to f of x, right? If y is equal to f of x, let's think of something more than just, we can just hide this thing. Okay. We can just do more than just y is equal to mx plus b, right? So the first complication we talked about is, what if x is not one x? It's not one quantity, but a set of attributes. Let's say there are 5 of them, or 10 of them, or 20 of them. So in this case, this is where you talk about multivariate model. Okay, so x is called a variable. Why? Because just like I told you, once you decide on an f, right? F is a general thing, and then x is a specific, but it's specific only for that instant. So tomorrow it could be another value, right? So it varies. That's why it's called a variable. To make it clear that you start with x, sometimes it's called independent variable, meaning x just comes first. And then once you plug x into the f of x, you get y. Y is a variable as well, right? But it's a variable that depends on value of x. So sometimes it's called dependent variable. Okay. In fact, in grade school, you usually start up with that terminology: independent variable, dependent variable, and so forth, right? So that's the first generalization. So this is the concept of vector. Again, we'll write like this in Mathematica, but you can visualize it as a stack of numbers, a stack of number. Now, if the function you apply to happens to be matrix multiplication, then it is linear algebra. Technically, by the way, it's called a fine model, but I'm not going to burden you with that. But basically, you just multiply it with a matrix, okay? And then maybe you add something, okay? Now, strictly speaking, by the way, if you don't add anything, it becomes a linear model. If you add something, it becomes a fine model, okay? That's just a technical word in mathematics, okay? The point is, by the way, does the dimension have to match? Yes, the second one has to match. Does the first dimension have to match? No, it doesn't. So you can multiply to an n-dimensional vector with a k by n dimensional matrix. Then you get a k-dimensional object at the end, right? But most of the time, this will be a square. Most of the time. Okay, but doesn't have to be. Okay, it depends on your application. So that's why I put m by n matrix, but in particular, m is equal to n. So that's a whole thing of linear algebra. Linear algebra allows you to build a fine model. So anytime in life you come into a situation where you can model the left-hand side by an affine model or matrix multiplied by vector plus another vector, that is what you use. Okay, that's what you use. Now, but why do I teach? In real life, chances are a fine model is not going to get you much in life. Okay. So why do I teach linear algebra? Why do I stress on the importance of algebra? Because more complicated models often use affine elements. So in other words, within this giant function, there is kind of like matrix multiplication in there somewhere. There's a vector addition somewhere in there. In fact, the most advanced machine learning neural network is a little bit like that. It's not an affine model. So linear algebra is not enough. But when you open under the hood and you look to the nitty-gritty details, there's a lot of matrix multiplication in there. There's a lot of vector addition in there. Okay, so that's why even though a fine model on its own is not going to get you far in life, okay, it's based on this basic, ax plus b kind of thing. This thing is going to be the basic component in so many advanced deep learning algorithm. That's why linear algebra is the foundation of that. You know what else? And this is going to surprise you. A lot of quantum computing is based on linear algebra. Mechanically. In other words, if you're going to do the mathematics of programming a quantum computer, you need to do a lot of transformation that's expressible as a linear, as a matrix multiplication. Really, it's like that. So it's quite interesting. Linear algebra not only is the component of virtually every single deep learning model you are going to use in your lifetime, it's also the basic mechanism of doing quantum computing. Okay, so if you had an opportunity to deep dive into linear algebra, maybe just take a linear algebra 101 from your from Department of Mathematics. Do so, because you will never outlive the usefulness of linear algebra. I can tell you that. Okay. So got multivariate. So if it's multivariate, but in the linear, then it's special. So this is a special case of that, right? It has the same feature over here, but it has another addition. Okay. Now, the other thing is called, these are not, again, mutually exclusive. This is a class of model. So you will see the word time series model. Now, again, time series model, like deep learning model, has a lot of matrix multiplication in there. Okay, but I'm mentioning it here separately to underline the fact that when you talk about time series models, it's a series in time. Well, obviously that's in the name, right? You know what series is, right? One after the other with some kind of indexing. It's indexed by time. So stock price is a time series, right? COVID case is a time series, right? Anything, just about anything where you track over time is a time series. What it means is that you have some variable, okay, X, but instead of X being just the input, like dark cloud gives rain, it actually gives a value of something at a particular time, and then you index that time. So it is a set. Notice the curly bracket. So X is a set of value V at time S. Whole bunch of them, whole bunch of S. So price yesterday, price the day before, price the day 2 days before, price 3 days before, so forth. Y, on the other hand, is not something else. It's the same thing, just later, T. So think of it as, I'm drawing from left to right, right? So this is T. This is the value of T, V of T. This is the value of S, where S is equal to T minus 1, S is equal to T minus 2, minus 3, minus 4, minus 5, blah, blah, blah. Go from left to right, okay? But when I write here, it goes, okay. Right? So that's called time series model. Economists, econometricians spend, well, economists maybe not, but a lot of economists do. But certainly econometrician, if you have friends from econometrics department, they spend like 3/4 of their lifetime worrying about time series. Why? Because they work with quantities that measure the well-being of an economy. Now, it's no good to say that we were happy 10 years ago, we had lots of money, we have no money now. So this kind of economic, financial well-being is always in time, right? So that's why econometricians spend 3/4 of their lifetime studying time series. In fact, you know, they just call it time series econometrics. Okay, so that's a time series model. Again, I keep saying this, there's a lot of matrix multiplication in time series model as well. So you can't get away with linear algebra. Okay, you can get away with a lot of things in life. I told you that, you know, you don't have to put a lot of effort in your undergraduate, but definitely you have to learn your linear algebra. Fine. Okay. Oops, sorry. Let me. Now, next we go to what's called dynamic model. Dynamic in this case, well, it's a little bit like time series. Dynamic in this case means it's not static. It's not, it changes in time. Okay. Well, it's not time series in this sense. It's dynamic in the sense that we talk about in physics. Okay, dynamical system, kinematics, dynamics. In physics, the difference between kinematics and dynamics, actually, to be honest with you, if you look at it this way, this is not called dynamic model. It's called kinematic model in physics. But anyway, to the rest of the world, it's called dynamic model. Well, dynamic models means you're not having one X and one Y. X and Y are actually the same thing, but one is the quantity itself. The other one is the rate of change. The other one is the rate of change of the rate of change, right? So in other words, if X is a position, right, then you're trying to relate something else that's quantity derived from changes in value of X. So in this case, if, for example, instead of Y is equal to f of X, I would write something like X dx dt equal to X, something like that. Okay, so the right hand side could be X, could be whatever. So I'm trying to relate this kind of thing together. And in differential equation, sometimes you write the speed on the left, sometimes you write the position on the left, sometimes you write the speed and position on the right, or whatever. It doesn't matter. It doesn't really matter. Okay, there's usually a convention of where you write, how you write this. Usually you write the derivative on the left hand side, but the point is you relate them. You relate them. So you can think of this as something like that. Okay. See, I write it here. Y is velocity of v of t. X is v0. So let's say v is a starting position. V0 is starting position. Vt is position in time. So when I write it this way, I say position in time is a function of where you start, your speed, your acceleration. Now, like I said, it doesn't really matter. You can switch this around. You can say, you can put the acceleration on the left-hand side and put initial position, current position, and speed on the right-hand side. It's kind of interchangeable. Okay, so that's the differential equation. Right. So now we got this. This is our dynamic model with ordinary differential equation. With partial differential equation, it's a little bit like when you apply this kind of thinking, but instead of one X at a time, you have a whole bunch of them. So it's more complicated. It's multivariate calculus. Okay. Now, let me clean up a little bit. Okay. Now let's move up to probabilistic model. Okay. Now this is where I'm going to spend a little bit of time Monday, or maybe today, but maybe Monday. Probabilistic model is you're still modeling Y as a function of X, but you know you're working with something that is so uncertain. You can't narrow down. It's so uncertain. So the best you can do is not saying, if I throw the ball over here, in 2 seconds, it's going to land over here. Instead of doing that, let's say it's a very poorly maintained cannon. Okay. So instead of being able to precisely calculate, if I have initial position, initial velocity, and the angle, I can tell you what the bullet is going to be in 5 seconds time. Instead of doing that, I know it's going to be around here, but it's going to be sort of like between here and there. So it's sort of like between 100 and 120 meters. Okay. It's somewhere around there. So you know definitely that there is a kind of a probabilistic statement you can say. So you can never, ever, ever, ever say Y is the quantity. The best you can do is Y is the probability of some quantity being certain value. That's called probabilistic model. Okay. So I write it in process. Y is a probabilistic statement about some quantity X that we expect to be able to serve, but we can't tell for sure. Stochastic model, and you're not going to get to that, but that's the one that got the Nobel Prize, right? With Black-Scholes model. That's kind of like combining differential equation with probability. So it's a little bit more interesting. Okay, just as you have the dynamic model, you can relate, say, position with its velocity, right? In this case, instead of having the position, you have uncertainty as a quantity. So uncertainty grows with time. Think about it. Yeah. If you have the dynamic ordinary differential equation, like the amount of money in your bank, you put in and you have compounding interest, well, you have money that grows with time, right? In this case, you have uncertainty that grows with time. So you model that with differential equation that has a very peculiar function of feature to it, and that's called stochastic differential equation. So that's where you're not going to deal with that. In fact, most finance students don't even deal with that. Only specialists in financial engineers. Now let's get to our more relevant to context. The difference is, like I told you, you had to pretend. You know, I asked you to pretend. Your job, you're not a computer engineer, so you don't build computers. You're not a data professional, so you don't supply the database. You don't maintain the database. But you are an analyst, or you can call yourself a data scientist. Your job is to come up with the F that best fits what you observe as a pairing of X and Y in the past. So you come up with the best F, okay? Like I said, 50, 100 years ago, economists has to use logic, the power of logic, maybe consult with psychologists or something, and come up with the functional form, handpicked. The difference with you guys now is that we don't operate in that way in most of the application. Nowadays, we say, okay, instead of all the millions infinite possibility in mathematics, I'm going to think of a function that will fit my data. So this is my F. Instead of doing that, I'm going to say, of all the possibilities, I'm just going to narrow down a little bit, not so much. So it's not quite infinite, but it's practically infinite. And I ask the computer to check. Now the computer is going to run through the combination, right? Now, in theory, what can happen is, let's say I have 1,000,000 possibility for Y, for F. I just ask the computer to try all of them, see which one works. Okay, that's kind of brute force, try everything. Well, that's impossible. It turns out there are too many variations to try, even for the fastest computer. So what the computer does is exactly what we talked about yesterday, right? Gradient descent. Okay, trying everything is like this. It's like you have a forest. I look at every single inch of that forest and see which one is the lowest spot, and that's my minimum. Okay, that's impossible to do even for the fastest computer. Can't try everything. So it tries one thing, takes a gradient, tries another one by taking a step, try another one by taking a step. So obviously we saw the picture yesterday, right? Where I had this kind of this. Now, instead of every single point being examined, computer examine this point, they go to this point, they go to this point, they go to this, maybe 1,000 points, but certainly not gazillion points. Yeah. That's what machine learning does. So it's replacing the hand-picked with the machine trial. And that process is called learning algorithm. Okay, and that's where, so just as, now this is a little bit meta, by the way. I told you guys, right, that you have a better model or you beat your competitor if you have a better model, if you have a better F. Well, in machine learning world, you beat your competitor if you come up with better algorithm so that when you apply to the data, you get the better F. Does that make sense? Does that make sense? Right? So it's like, if you compare movie, this movie is better than that movie. If you go meta, it's like you're comparing the director. This director is better than that director. So if you hire this one, he's going to make the model that movies is better than the other guy. Okay. So machine learning algorithms a little bit like that meta level. You know, you pick a director to produce a better movie. You pick a better learning algorithm to produce a better machine learning model. Okay. So that's where the art is. That's where the competition in the fierce machine learning space, you know, is. Now, finally, we get to this thing called AI-driven model. Now, let me circle here. in a very limited way. When you hear AI, you should say something like, it's an F that somehow helps your digital application work seamlessly or naturally with human being. So in that case, the only thing you want from the F is to give behavior of a human. So if X is input, in this case, the input is Alexa, how are you? Go in. F, produce Y. Y is actually a sound saying, I'm fine, thank you, and you? Right? So it's kind of a natural feeling. So that's what AI model in itself just does that. Just sort of like gives you a nice feeling of working with a human being. So that's what chatbot, that's what all kinds of stuff come in. But if I'm talking about AI driven, okay, not just an AI. In fact, there's this course called something like Apply AI or something in Basa as part of your core tech. In that case, it's a bit like this. You're applying AI at this level, okay? So whatever business you're in, you want your user or your customer to feel that they're talking to a human being, they're interacting with a friendly advice or kind of thing. That's what Apply AI in that sense means. Very narrow sense. But even that, by the way, 20 years ago was very difficult to achieve. Okay, this is called AI that passes the Turing test. Turing test is where, forget about the sound because the computer sound is still not convincing. But let's say if you communicate with each other by line, right? Well, if you communicate by line, you know the other person is a friend, right? Well, let's say you communicating with a line representative of a company. You don't know that person individually, but you can discuss, you know, I bought this product, it's defective. Can I return it to you, please? No. Okay, then can I get store credit for it, please? You know, you're chatting with your account customer service. Well, if that account service is actually a computer, you can't tell the difference. It's called passing the Turing test, named after Alan Turing, the hero of well, it's actually father of modern computing. Okay, so if you can't tell that you're talking to a computer, that means passing a Turing. So this Apply AI is sort of like, think of it as chatbot or something like that, right? But when I say AI driven, I'm actually referring to machine learning model, except within machine learning model, there are algorithms that is inspired or is based on some kind of mathematical or theoretical foundation. If the underlying approach is based on function that has the flexibility, has kind of intuitiveness of a human being. In other words, machine learning is like an algorithm that builds F. But if I design the algorithm so that F itself, the way it learns is very natural. It's like learning from experience. Not only is it learning from experience, it has certain flexibility. It has ability to sort of like make guesses. You know, computers are not very good at making guesses. So if you build F that is as good or as if it were a human being, it's called AI-driven model. Okay, so that's in that case. So that case is not about the natural conversation. Okay, for example, let's say you are more intuitive. You're more intuitive. You have hunches that, you know, this is, let's say it's not dark cloud. It's not dark cloud, but you still have a hunch that, yeah, it might rain or something like that. It's that kind of intuitiveness. The model that has that feature, that has ability to do that, is built, engineered to mimic that kind of human reasoning. Okay, and that's kind of AI-driven model. Now, the AI-driven model is just that. It's a machine algorithm that has a reasoning capability similar to human cognition. And then there have been many approaches to AI. Historically, there have been two approaches, two large camps. One camp just sort of died. And the camp that you live with today is the neurocognitive or deep learning camp. Okay. So there have been different kind of AI in the past. There have been different kind of AI. Okay, but nowadays AI is invariably built around deep learning architecture. So that's the world we are in now. Okay. So with that, now we haven't got much time, have we? What I want to do is, like I said, let's see if we can do this. Now we have like a 2 more class. The way we're going to do is there are two more things. There's one more thing I want to do, and then this. One more thing that I want to do is go over a little bit about probabilistic models. The reason I want to do that is because not everything is solvable by machine learning. In fact, most of the simple questions that you do with client profiling and so forth, it's just more statistical than machine learning. So I'll give you some of that. So I'll talk about probabilistic model a little bit, right? It's sort of like how you don't try to say where things is going to be, but sort of like roughly speaking, what's the likelihood, the probability you're going to see it between this value and that value. So I have to do that, but I might as well do it on Monday. What I want to do is start getting on this kind of random sampling of students and ask you to come forward and talk about what you, I guess, study as the Mathematica. Okay, so we'll do a little bit of that for however many we can today, and a little bit of Monday. And finally, I think for the last class, it would be even better if instead of just bringing up some Mathematica demonstrator program and talk about it, we can talk about the idea that you might have, the problem you want to solve, things that perhaps would be something that starts with your project seed and finishes your senior year capstone project. What I would do is not to help you with the project. Obviously, that's the whole learning process. But what I want to do then is to say, haha, this problem has mathematical element to it. Basically, just sort of like do a little bit of a show and tell that, oh, you interested in this problem? Well, there'll be matrix multiplication here, 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 and here. There'll be calculus here, 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 and here. That sort of thing. Okay. So it's sort of like a preview of the mathematics you're going to need to solve your project challenge. So that's what I hope to do anyway. So let's start with somebody. Okay. Ithi Yapa. Inti Yapa. Bun Jaran Sumbat. Where are you? There you go. Come up. Okay. So what I want you to do is come up, maybe put a little gel on your hand and sort of like go to the, well, presumably we have we have internet on here, right? So let's do that. Okay, so let's go to internet. Oh, we launch Zoom. Nope. Okay, so Mathematica demonstration project. Okay. Okay, so a little bit of gel in your hand. Very good. And here, and then go to the one that you picked, the one that interests you, and tell us about it. Great. Very great. Okay, excellent. Okay, Pat?
So I'll show like the difference first. So the nominal diameter, so if it's like less, it will be a different like shape. So as you increase, it will expand more like this, and the part of the torus It's like here, but if you increase it, it'll be like this. So part of the ring is like obvious. Let's see like this. So how it is related to mathematics is like, for example, geometry is like a shape of like circles and diameters, and also like cylinder over here. So I found it interesting because at the beginning, I don't know like what's the difference between like low amount of nominal and diameters and like high amount. And also I got to know what does like torus means after I like tried to like learn and change with it. So in the future, I can know like how to like use a ring or like apply in real life like that. Thank you.
Okay. So very good. Actually, I want. Okay, this is a good start. It's a good example. Now, here's what I want you guys to do. Okay. Well, first of all, this is very good. You know what a torus is? Anybody know what a torus is? Beside her? Well, torus is a geometric shape, just like a cylinder, right? A sphere, that's a geometric shape, right? A cube, a box, right? A torus looks like what you do when you take a tube and join the end together, right? Now, technically speaking, if this torus were made, okay, let's start from here. If this torus were made of a stretchy material, right? You can stretch it. You can stretch it, right? You can stretch it lengthwise and here and there and so forth. What does not change as you stretch? Well, if you imagine, okay, now watch my hand. Okay, I might as well use the okay, let's make it a little bit bigger and we'll go to that. All right. So if, right, on the surface of a torus, I put a little dot here, right? And I put another dot here, put another dot here, and I put another dot here, okay? And make some kind of grid reference. Okay, watch this, right? Now, I'm not gonna do it here because the program probably doesn't allow me to do it. Just to show a fixed torus. But if I stretch it, the location of all those dots is gonna change, correct? But if you imagine that between those dots, this is the connection. This is like a string or a line of communication, right? So this guy say, to my left is this guy, to my right is this guy, to my front is this guy, to my back is this guy. That will not change. So this positional thing would not change, right? Now watch this, watch this. What if I do this all over the torus, okay? And has 20 marks, okay? And I go around as well. And I have a 10 points, right? What's gonna happen is I can take a piece of paper, think of this as a torus made of paper. I take scissors and I chop it, cut it. Look, it's a rectangle. Okay, it's a rectangle, but that's not all. That's not all. How long is this thing? It's 20 grids, right? Grid points. And here is 10 grid point, let's say. Okay, so I cut it, right? I cut it. Okay. This, again, if you're over here, your neighbor will not change. Okay, just remember this is my right neighbor and so forth, right? My first, second, third, fourth. This will be the same. So as I stretch, it's the same as if I have this rubber sheet and I have the grid and I stretch it, right? The distance, the actual physical distance will be different, but the fact that I know who my neighbor is will be the same. Okay, this, by the way, in mathematics called topological preservation, but forget it. The point is, Tell me one thing that's different between this and this. Well, this, I can represent position as I and J, right? Just like a matrix, right? I, J. The difference is here, I have an N. With torus, you curve back. And you can curve back in both dimensions. Okay? Right? Curve back in both dimensions. What does this remind you of? Well, think about it. Okay, let me ask you another question. Are you a flat earther? Any of you believe in flat earth? Hopefully not, right? Okay, well, consequence of not being a flat earther is that you never fall off, right? You never fall off. Can you fall off? A torus is exactly, well, not exactly, but in that sense, a torus is like the surface of the earth. In other words, it's not in a lot of ways, but in this way, it's not, because it's the same, because you have no beginning, you have no end. You can't say you start at North Pole because that's just the way we draw it. We can actually start North Pole here, right here. I can say this is the north, everything else is south, right? So you never fall off. What's interesting is that the earth is three-dimensional, but you on earth is two-dimensional, right? You can't fly, you can't fly, you can't fly, okay? And let's say the surface of earth is flat. Even if it has mountain, you are not flying. You're still climbing the mountain. You're still walking east and west, right? So torus, same here, is a two-dimensional space embedded in three-dimensional space. Okay? So torus is a lot more interesting than you think. So that's mathematics. Okay, that's mathematics. Now, what this means is once it's a mathematical object, once it's a mathematical object, I'm telling you beyond this. Let's say your project is, for some reason, product design. The product design, okay? Because this is a mathematical object rather than just a picture you draw, Mathematica knows the functional form of this. Okay? And supposing I want to design a ring that has certain circumference, right? Has certain weight, has certain attribute, blah, blah, blah. You don't have to do all this trial and error. You can actually ask Mathematica, for example, let's say, let's say this is made of gold. This is made of gold, okay? It's made of gold. Design the ring that would use this much gold that would cover the finger of this size, but no more. So you don't want to waste gold. You want to minimize the amount of gold. So you can actually ask Mathematica to solve for the circumference exactly, because it's a mathematical object. So this is very, simple, silly little thing. I want to show you how exactly it works in the project arc of your life. See what I mean? So obviously, plastic is a lot cheaper than gold. But right on the fourth floor, we have a 3D printing machine, right? Same thing here. I want to print something in 3D. I don't want to use up a lot of plastic, right? I told you maybe you didn't get the picture last time, but exactly the same story. If I want to make a shape of a rabbit, but minimize the internal, maximize the internal volume so that I don't waste a lot of plastic for my 3D printing, I can use mathematical function to do that. Same here, okay? So with very high degree of precision, you can calculate exactly what's the thickness or the diameter of the ring you should make to minimize amount of gold, okay? So if you have a specific amount of gold, it's what? It's one solution, okay? Remember I told you, no solution, one solution, infinitely many solution. Okay, what is no solution? No solution is, for this finger, you don't have enough gold to make the ring, okay? One solution is, I have this much gold, happens to be enough. What is the diameter? Okay? Now, infinite solution means Well, I can allow for different amount of goal, but I want to maximize something else like elasticity. Well, goal is not that elastic, but you see what I mean? Yeah, there's some objective function like I want to maximize the surface area so that it appears shiny. Okay, but not so much that it becomes expensive. Okay, so now you have infinitely many solutions. You do what? Optimization. You choose among the infinitely many solutions, the one that's best. So the one that the best, maybe it's not using the minimum amount of gold. It's using a little bit more than minimum amount of gold to make a ring, but it's big enough to look big, but not too big or something like that. And they do that in jewelry design. Why? Because diamond's very expensive. Okay, diamond's very expensive. So you want it to look, okay, but you don't want to waste a lot of diamond, especially in what's called pave cut, meaning they put diamond like tiles, like pavement. I don't know if you've seen those. But... okay, so this right away tells you that if you think of your thing being your project, your object, whatever, as a mathematical description, you can do literally optimization on it. In this case, your optimization is to minimize amount of goals or whatever, it doesn't matter. But I don't want you to just do this. Okay? I don't want you to just do this. This is actually what I want to do. And go ahead up. For Monday and for other days, you should do this. Okay. If you say, dialogue. Okay. If you download to desktop, okay. If you download to desktop, let's do this. I download to desktop. Okay. Don't show again. I'm going to get this guy. Oops. I'm going to get this guy. PDF. Oh, CDF, sorry. Desktop download. Okay. CDF. Okay. That's called computable document format. So even if you don't have a Mathematica program and you just have a player, you can play with it. So this is what you can do. Okay. That's not what I want. That's not good enough. Okay. For most of the time, it's a player. Okay. So you can play around with this as if you have the Mathematica program. Okay. So that's not interesting. It takes a while. Okay. Now, what I want you to do is instead do this. Go to source and download to desktop. So if you download desktop by default, it's just going to download the CDF. If you go to source, that means the actual code, right? And you do the same thing, download to desktop. Okay. You're going to get something else. Why did it keep, okay. It keep asking me if I want to download. I don't want to not show again. There it is. Okay. So it becomes, instead of .cdf, computable document format, it becomes .nb, your notebook. What's cool about the notebook is you get the same thing as before, but let me unhide this. Okay. If you click here, notice this is all the kernel. Okay. It's actually hiding the code. So if you double click on here, it's going to show you the code. So imagine, right? I don't want to draw this picture. I have my own design, but I want to exhibit this kind of thing. I can do something else. For example, I don't know if this is going to work. Okay. But let's say something like, okay, this is going to probably give me an ellipse. Okay. But you know what I mean? The point is that you can copy the homework, right? So this guy, you find something that's very close to what you really want. Oops. Yeah. Anyway, it has all this. The point is the manipulate you're familiar with, right? That allows you to play with few things. ID. Okay. So if you look over here, this is it, right? Nominal diameter. Okay. That's the name of the button. It goes to the variable names ID, initial default at 3, changes from 0 to 4. That's what this manipulate mean. I just haven't used it. Okay. So this is a variable called A, default setting to 0.2. The name of that variable I want to show as part of torus. So that's this one, part of torus, going from minus pi over 2 to 1.5. Okay, that just happened to be my setting. So this is it. And what I want to do is here. This is my action. Okay. So you can learn a lot from copying. Okay. And this is completely valid. I mean, they're not trying to say, oh, please don't copy me. I do my own Mathematica demonstration, and I show people so that in the banking world, they can copy it, right? So let's say Basel. So, okay, this is a capital adequacy calculation that all banks in Thailand have, well, not in Thailand, all over the world has to do. So when I was in the Bank of Thailand, we had to sort of communicate this idea to the commercial banks, because back then, banks just use accountants, didn't have any risk, some risk modeler, but not so many, and they're having tough time. So basically, this is the calculation of the minimum capital as a function of certain parameters. Okay, so I did this. I publish it online. Somebody else can, March 2011, somebody else can download to desktop, right? And use it in their banks. So we make this sort of like a public service kind of thing. Okay, so it's not, this is a very open share kind of feeling. Okay, likewise, I want you to do exactly that. So we only got one guy today, one girl today. So commendable to you. Very good, Kap. Naka. So yeah, you choose an interesting one. It has a lot to expand on, but this is what I want you to do now. Not just the CDF, but download the NB just to see if you can read it and see if you make sense of it. Okay. So I'll see you on Monday. We'll continue this exercise. I'll talk a little bit about probability modeling. Okay. And that will see you out the rest of the pre-course. Okay, Kap. Very good. I'll see you on Monday.